Welcome everybody to the April 2026 meeting of the Mornington Peninsula Astronomical Society, and as usual I go through one or two of the things that happened in the last month since we've been here. The obvious one is Artemis 2, which has been done to death on TV, so I won't go into it too much, other than to point out for those of you in the room that are my age or around that you'll be familiar with the command module that was used in the Apollo missions, sort of shown down there, and to scale the one that was used in Artemis. So as you see, it's considerably larger than the Apollo one, which had 3 astronauts shown in white there, and 4 in the Orion module. Notice one actually sits elevated relative to the other. So quite a lot larger for those 4, being cooped up for over 9 days, almost 10 days on the way out to the moon and back again. Now Artemis 2 didn't actually land on the moon. It did basically what Apollo 8 did, and Apollo 8 had Jim Lovell shown up here in the top right hand side, and he was not only on Apollo 8 but he was also the commander of the ill-fated Apollo 13 mission as well. So he did the Tom Hanks role, if you like, in the movie of Apollo 13. And he died last year, but a few months before he passed away, he actually recorded a secret message to be sent to the crew of Artemis 2 on their way to the moon when they got around the moon. And this is what he said. Pre-recorded, NASA transmitted it up to them at the time. Went, hello Artemis 2, this is Apollo astronaut Jim Lovell. Welcome to my old neighbourhood. So in other words, it was in his voice, and they recognised his voice. He then spoke about Apollo 18 orbiting the moon. He saw that famous picture there, which was called at the time Earthrise. And the Artemis 2, when they were in a similar sort of position, also photographed the moon, and it was more of a crescent shape because the moon was a different phase at the time compared to when Apollo 8 flew around the moon. Then he said he was proud to pass on the torch to them, and not to forget to enjoy the view while they're there. Don't be too focused on doing what you have to do. Then he finished with good luck and Godspeed from all of us here on the good Earth. So that was transmitted up to them on the 6th of April as they flung around. So Artemis didn't go into orbit around the moon. It just basically went a couple of times around the Earth. Those who were at the meeting last month would have seen the orbits that we showed. Went around the Earth a couple of times, then across to the moon, similar sort of path to the Apollo missions, where they go like in a big infinity sign sort of shape. Went once around the moon, further out than the Apollo missions did. The Apollo missions came in fairly close to the moon's surface, whereas in this particular case they didn't. They were quite a way away from it, and that's how they got the distance record of being the furthest astronauts away from Earth, by the mere fact that they went around the other side of the moon and quite further out before using the moon's gravity to fling them back to Earth. So they didn't actually go in orbit around the moon. They just sort of went once around it and then came back. So they're still learning the new craft. Now, one thing that they did actually encounter when they were up there was they saw a solar eclipse. So in other words, when they're on the opposite side of the moon from the sun, they basically had the first space-based solar eclipse that is being witnessed, and there'll undoubtedly be some in this room who've experienced one of these things from the Earth's surface, but certainly not from space. Now the other thing they had fun with the toilets on the way. The Apollo craft didn't have any toilets at all, and what they ended up doing, and particularly even as the astronauts, when they got to the stage of walking on the moon, they just basically had big nappies on. Right, and they just had to put up with when they needed to go. They just had to go wherever they were, and so that was very crude way of actually getting to the moon and coming back again. But it did the job sufficiently. So no plumbing to worry about, no things going wrong, because of course in space you can't have toilets the same way as here on Earth because there's no gravity. So in other words, you have to have pumps and suction and all sorts of things to try and draw it away. Otherwise, you're going to make a big mess of the inside of your spacecraft. And electronics tend not to like conducting fluids flying around it. So what the backup plan was when the toilet failed on Artemis 2 was they used one of these little devices here, which is known as the CCU, or Collapsible Contingency Urinal. Now it's called a urinal, but this is actually the female version of it here. And what it is basically a big bag of gel that under capillary action draws the urine into it and up towards the end of it. So it doesn't rely on gravity at all, doesn't rely on any suction, it just purely relies on capillary action to pull it up. And you see, if you look really, really closely down there, you'll see like a typical garden hose connector that you'll get on your garden hose at home. And although they didn't show it in that picture there'd be a different attachment, I would imagine, for males and females to connect to that. But that was generally what they used as Plan B, and they took several of those along with them, just in case things didn't go well. And so that's what they used in the meantime. After obviously the success of this mission as coming back, it was then announced over here, the table's probably a bit too small to read, but the White House has actually proposed cutting the budget for 2027. In the wake of a success, they decided to propose that they almost halve the science output of NASA. So in other words, cut all the missions by 47% and 23% overall. And in the case of when Apollo went around the moon, they had a hookup with the existing president at the time, who was Richard Nixon. And very sort of telling that Richard Nixon, and the one that they spoke to this time was Donald Trump. So you could think peas in a pod there. And one of the things he decided to make in his monumental speech to them was to actually let them know in his first term he actually seriously considered removing NASA, deleting it entirely, getting rid of the whole thing. And so you can sort of see the mindset there. So the current budget there, 2027, is proposed to be 50% less. Hopefully their parliaments over there, the two houses, will block that in some way. And these are all the missions that are going to be cut as an immediate result of it. So 4 columns here, there's astrophysics, there's things to do with the Earth, things to do with the Sun, and things to do with the planets. And over here, certainly without looking at it, I recognise some of these. So there's the Fermi mission, Chandra mission, which are like X-ray telescopes. Some of these are well and truly already been launched and are working out there, and this is just pulling the plug on them and just letting them go, which are total waste when you think about it. You've gone to all the trouble and expense of getting them up there, and this is all just about cutting the mission. There's LISA, which was a gravitational interferometer in space as well, orbiting that. Where's some of the others? Euclid, which has already been launched. That one's looking for dark matter and what is actually dark matter. So you wouldn't be able to find any of that. In the Earth Sciences ones, these are all ones to do with weather monitoring and climate monitoring and sea level monitoring. So it's a sort of thing that if you're trying to hide what's going on here on the Earth, that's what you do. You take away the eyes so that you can't actually see what's going on. And for example, there, the Discover satellite there, actually we use a picture of it in our presentation on the solar system to schools. And it shows a picture of the far side of the moon in front of the Earth, with actually Australia in the field of view, and that was actually taken by the Discover mission. So in other words, they're considering even abandoning that, which views the whole Earth at any one time. Some of the other ones here, if I can see, the helios physics ones, in other words, the ones to do with the Sun. There's several new ones there. There's SOHO, which is the Solar Heliospheric Observatory, which has been in place a long time, discovered lots of comets smashing into the Sun, and also looks for particles coming towards the Earth in an outburst. That would have the plug pulled on it. And in the planetary sciences, you've got New Horizons, which was the one that flew past Pluto. Basically, pull the plug on that and let it go, turn it off. Absolute crazy. Mars Odyssey and Maven, which are all around Mars at the moment. So basically, they would have the plug pulled on, even though you got the thing in orbit around there. And Mars Express as well. And of course, last year they cancelled the one to go and collect the samples that were that were being left behind by the Perseverance rover. They cancelled the mission to go and bring those back to Earth for study. So they're sitting in their sample containers on the surface of Mars at the moment, and at this stage they don't know when they'll be brought back, if indeed at all. Very, very sad. Okay, so tonight, welcome to the meeting, and we've got a couple of new members here. New members since we last met are Claire McKenna, Jan Kendall, Mark Hanson, Natalia Banks, John Hedge and Stephen McAndrew. And you want to put up your hands if you're one of those new members? Yep. A couple. I'll get the committee members to put up their hand. Normally our secretary would do that, but she's not here tonight. Feel free to contact any of the people there, and we'll try and make you as welcome to the society as we possibly can. As usual, I'll go through the events of the past and the coming months, then throw over to Chris for the monthly photo challenge. Guido's not here tonight because he's in Germany at the moment, but he's submitted his sky from the month from Hamburg Observatory, and you'll see that shortly. Then we'll look at the magnetic universe. So most people, when they think of telescopes and that, they'll think visible light and maybe infrared light and X-ray radiation and other electromagnetic radiations, but it can also be observed and studied with magnetism as well, and that's going to be given by Professor Katherine Blundell from Oxford University. Then we'll look at the basics of orbital mechanics, given that we've seen Artemis go, and this goes through things like Kepler's laws and Newton's laws. Tries to give you a quick primer on that, so you'll understand what's actually going on with the spacecraft. Now that video is a little bit dated. It sort of shows the shuttle in there, but the physics behind it is exactly the same, and that won't change. And then we'll close by looking at a couple of the missions that went around Earth's Van Allen belts. There was a Sampex mission and the Van Allen probe, twin probes that went around the Earth. One of them actually re-entered Earth's orbit just last month. So of those twins, there's only one still up there. Neither of them are actually functioning. They've run out of fuel, and so it'll be an uncontrolled re-entry whenever they come in. So one came in last month and the other one's predicted to come in sometime in the 2030s. And then we'll close. All right, so recent events, 20th and the 21st of March, some members of the Society went down to Inverloch for their Inverloch Equinox Festival, and they had about, over the 2 nights, about 140 members of the public there, mostly Cloud, and Chris Morley from the Latrobe Valley Society gave the talk at that one. Telescope Learning Day we had simultaneously on the Saturday with that here at the Briars, and we had 70 turn up for that one and 10% Cloud, and that went quite well. Then committee meeting on Zoom the following week. We talked about the emergency management plan, which Phil and Ali are drafting at the moment, and Rabbit Gate, which was our little gate. You probably passed some rabbits on the way in. I passed at least a dozen myself and a couple of wallabies on the way in tonight, so they're out there. We've had 2 requests now actually for Year 10 work experience students to come here, both from quite a significant distance away actually, applied to come and work here, so still working on that one. Committee looked at insurance, and also a reminder for members who haven't renewed for the month yet is coming out, or may already have been done. Already done, yeah. Over Easter, from the 3rd to the 6th of April, I went up to the National Australian Convention of Amateur Astronomers held in Tamworth, and some of you who watch the ABC or the SBS might have seen a couple of the amateur astronomers there who received the medals from the Page the Page Medal from the Astronomical Society of Australia, and I'll talk more about that at the next meeting. I've not been able to put together something for that for this meeting in time. 3rd of April, we also had public night here at the Briars, where Trevor gave the talk, where it was almost entirely cloudy. So they'll come back at a later night. And the night after, on the 4th of April, which was a Saturday, we had the Shire Moon Night with lots and lots of kids coming across onto the society along a line of lanterns, I was told, along the back members' entrance into here, which would have looked lovely if we'd had a photograph of it. And no cloud that night whatsoever. And Manfred Berger gave the talk. And the next time we saw, that we here at the Briars, was for the public Indigenous night that was here about a week later. And some of the people that turned up to that Indigenous night had actually come from that Shire Moon Night, because they actually came up to me and said, please thank your speaker, which is Manfred, because he explained some things that we had no idea what was going on with the performers. And after coming to listen to him talk, he was only giving a talk for about 15 minutes or so, but in that time he cleared up some of the mystery of what was going on from the circus performers that were there. Okay, so what's coming up? This coming Saturday, we've got the Cosmology Discovery Group here at the Briars at 1:45, as usual. Members can just turn up for that one. You don't need to book. You'll be here in this room at 1:45 if you're interested in hearing what that's all about. They typically get around 20 people turn up for that, so don't worry about being alone. You won't be alone if you're interested in coming along to that. Just afterwards, there's the Working Bee and Members Barbecue here at the Briars, and after the barbecue, about 6 o'clock, Paul Albers will give an encore performance about defibrillation for astronomers, because we have one of these automatic defibrillators pinned on the wall next door at the Echo House. And so he gave this at the last meeting, but he's offered to come and get it in case there's a different lot of members turn up for the Saturday night rather than as come to these Wednesday meetings or look at it online. Then on the 25th and 26th of April, we've got a calisthenic club from Hallam coming here, and they'll be here all day on that particular Saturday and Sunday. So we'll have to have all the seats away and cover up the cameras inside. So they'll be doing calisthenic competitions in this room and also in the camp next door. So they'll actually be staying at the Briars camp, which is adjacent to us. So they'll be there all day and until about 4 o'clock, and then we'll bring telescopes here only on the Saturday night. And they're yet to confirm the time, but I suspect it'll probably be about 4 p.m. because they were a little bit worried that the young ladies that were doing this were going to be too tired for the competition the next day if they stayed late watching the night sky with us. So I said, well, at least come for the moon at very least, because it's about a first quarter moon. So the moon rises about 2 o'clock in the afternoon that day. So even by 4 o'clock it should be, unless there's cloud in the way, it should be visible. But I've given them the option of staying a little bit later, say about 6:30, and we might be able to show Jupiter, but they haven't yet replied to that. The May public night on the 1st of May, we've currently got 90 booked there, and Chris has kindly stepped in to talk at that one, as Trevor can't be here. 2nd of May, we've got the Eastern District Freemasons here actually at the Briars, and they'll come, I think, about 5 o'clock for a barbecue and have something like that to eat. So if members roll in about an hour later, there's only 30 books, so we don't need a huge number of telescopes here necessarily. 8th of May, we've got a new one which hasn't been posted out yet. Gregorius Lodge Freemasons, who visited us here at the Briars a few months ago, have actually asked that we do one up in Melbourne at their secret location, applying the appropriate secret handshake. When we know the location, we will let specific people know how to get into that one, and that one will be about 30 booked as well. 9th of May, which is the Saturday afterwards, we've got 2 things on. Those of you going up to see Brian Cox, and I know there's about 10 of us, That's on at 7:30 that day, so a reminder that that talk up in Melbourne is on the 9th of May. And simultaneously here in the Briars there's going to be a birthday party going on that evening as well. So members are not needed to gate crash that one, so you won't get any cake if you turn up. So that one's a private birthday party. 20th of May is the next one of these meetings here at the Briars.
And welcome everyone to Astro Mofo number 30. So the monthly photo challenge for the last month was open clusters. So those loose collection of stars that we see up in the sky. The first one that I'll show here, just as an opening image, it was sent in by Mark Stevens, and you may recognise that nebula there as being the Rosette Nebula. But in the middle of the nebula there is actually the open cluster. So NGC 2244 is the designation for the open cluster in the middle of the nebula there. Now it's in the constellation of Monokeros, or the unicorn, the single horn, Monokeros, that's what that means. The cluster is born from the material in the nebula, and it's quite a young cluster. It's around about 5 million years old, and it's around about 5,200 light years away. The largest stars in that cluster are around about 50 to 60 times the mass of our Sun, and they're about 400 to 450,000 times brighter than our Sun. So there's some really, really massive stars, and that's a pretty nice sea star shot there sent in by Mark, so good on you, Mark. And where Monokeros is right there. So you can see Orion on the right side, on the left side there, sorry, just setting in the west. Then you have Monokeros, then Canis Minor, and you've got Canis Major up to the top of it there. So it's in that part of the sky there, which is sort of just due north of us at the moment. So open clusters are collections of stars, usually about tens to thousands of stars, that are usually formed from the same molecular cloud, and they're all roughly created at the same time. So all the stars in the open cluster are roughly the same age. There's been about 1,100 of them discovered in the Milky Way so far, and obviously because there's parts of the Milky Way we can't see, we haven't discovered all of them. But the stars are in an open cluster are generally all loosely bound by gravity, mutual gravity, but it is a loose bond, so if those open clusters go past other molecular clouds, nebulas or other clusters, they do tend to pull apart and separate, and then their stars end up getting dispersed in the Milky Way. So they don't last forever, and our Sun was probably once part of an open cluster when it was formed and gradually just drifted away from it. Okay, this challenge was completed by Mark Stevens, as you saw earlier, Sylvie Grandit, Nick Axaris, Michael Barrow, Dennis Cook, Chris Kostokanellis, David Rolfe, Michelle Sykes and Greg Walton. So well done everyone. And this one here is it's actually a pretty cluster. It's by Sylvie, and it's the Christmas tree cluster. And again, also in the constellation Monokeros that we saw earlier, and that's with a C star S50. And what you can see in this image here, and I'll get the pointer up. Here we go. So we've got, up the top here, we've got what's known as the Cone Nebula, and that's sort of at the top of the tree, the Christmas tree. Down the bottom here, you've got this bright star, which is the trunk of the Christmas tree. And up here, that bright star there is the Christmas tree topper, if you like. And then you've got the stars coming down here, which form the shape of the Christmas tree, giving the cluster its name. So this cluster is, it's around about 2,300 light years away. Another one by Sylvie, we've got the GEM cluster, which is actually a really nice visual cluster as well to see through the telescopes. And this one's right next to the Eta Carina Nebula. So you've got over here, you've got the Gabriela Mistral Nebula, and up here, that's one of the lobes of the Eta Carina Nebula, which most of you will know the shape of. And over here is the GEM cluster. It's a really nice one to image as well, because it's got that nebulosity around it. And Sylvie got this with her Sky Rover telescope and 2600 MC Pro camera. So well done, Sylvie. And not much processing on this one. So just, yeah, and it still comes up pretty good. So that's still it's a really nice shot. Just shows how nice the shot is. And another one by Sylvie is a favourite of most of us, and one that's really popular on the public viewing nights, and that is the jewel box, Herschel's jewel box in Crux. So when you are showing this to people, you can now know that to tell them that there's about 100 stars in it, and it's around about 6,400 light years away. And if we want to know where the jewel box is, this is the Southern Cross here, Crux, and the jewel box cluster is just down there. This is where Eta Carina was, and we saw the gem cluster just up around there earlier. And this part of the sky is really rich in open clusters. There's a lot of really nice visually observable open clusters in this part of the sky here. The next one that I'll show you is one of mine, and I recently did a photo of the Coalsack Nebula, which is here, and if you have a look in the middle of it, just right there, there's a little speck which is the Coalsack cluster. So not really one that I knew about, but I did sort of note it when I took that wide field shot of the Coalsack, and I thought I'd have a closer look at it. And this was taken with a 200mm Newtonian and a light pollution filter, and there was a fairly bright moon at the time, so the light pollution filter helps to get rid of that. Now this one here, what we think when we say the Coalsack Nebula, we tend to think of it as a dusty cloud of gas and coal dust which blocks the light of things that are behind it. But light does get through, and this cluster is actually behind the Coalsack, so we are seeing it shine through the dust and gas that creates the dark nebula. And it's around about, what have we got? Do I say the distance? Yeah, so it's around about 4,300 light years away, and whereas the Coalsack is 586 light years away. One of the reasons that I decided to image this as well is, apart from it being in the Coalsack, when I was looking at the planetarium software, it showed that there was a comet passing right next to it. And I took the photo thinking I might be able to get the comet in the shot, but when I stacked and processed the shot, comet didn't turn up. And I was wondering why. So I re-stacked it using a different method, because normally when we stack images, it'll average out the pixels, and if there's a transient object going across multiple frames, the stacking software will ignore it, as though like a satellite or something like that. That's how we get rid of satellite streaks in our images. And because the comet was a transient object, the stacking software just used the average pixel value rather than the pixel value of the transient object, and it smudged it out. But there's another stacking method we can use where we don't smudge it out. So rather than doing the average pixel value, you just include all the pixel values in your stack, and we get the comet showing up right there next to the open cluster. So that was Comet 2025 A6 Lemon, and at that point when I imaged it is around about 1.95 astronomical units from us, so around about 291 million kilometres. So just something else interesting about that shot. And just that you can get these faint comets and these faint objects appearing in your shot, but there are different techniques to use to get them to show up. And that movement there was actually between about 12:15 and 1:40. So that's those individual shots that it shows up in there it's only about an hour and a half worth of travel. Okay, next one of mine was M41, or the little beehive in Canis Major, and we saw earlier where Canis Major is, the big dog next to Orion there, and this is also with a 200mm Newtonian and my astronomical camera, and 24 2-minute shots. So M41 is around about 100 stars in that cluster, and it's around about 2,300 light years away. And the last one I got was M46 in Puppis, so in the southern sky. And this one's M46, yep, 200mm Newtonian again. And the interesting thing about this one is that we have a little planetary nebula in there. So the planetary nebula is a foreground object. It's around about 1,300 light years away. And the open cluster is about 5,000 light years away. And this one here is also a nice one with a telescope to look at as well. So these are all things that you can easily look at through some of the scopes that we have here, or if you've got one at home. Okay, Dave managed to get this one here, NGC 2516, or the Southern Beehive, or I didn't know that, but it's also called the Diamond Star Cluster, and this one's in Carina. And this one's from Dave's remote observatory in Starview Farm. So he's got a V200, which is a Cassegrain telescope, and a monochrome camera, and he's taken some red, green, blue frames, 2 hours worth on each filter, and combined them for this image. So nice spiky stars there. Nick Axaris got this one here, the Pearl Cluster, and this is also a really nice one to look at through a telescope as well. And this is with a 130mm refractor and a light pollution filter. The L Pro filter is a light pollution filter, so it cuts out a lot of the sky glow and moonlight if you're shooting around that sort of time. This is about 30 minutes of exposure and 137 stars in this cluster. And again, like I said, it's a nice one visually as well. And this is Michael Barrow's version of the same cluster with a C-Star S50 processed in Cyril as well. So slightly different field of view. You got the that one there and that one there. So well done. Next, Dennis Cook has been very busy with his C-Star, and he's sent in quite a few nice photos of open clusters. And the spiky stars are added in processing, because the C-Star doesn't actually have a spider on it to create the diffraction spikes, but you can add them in to add a nice effect to the photo when you do process it. I think it's a feature on the C-Star that you can add in the diffraction spikes. Is that right, Dennis?
I use a little cross here.
Oh, to put over the scope? Oh, okay. Yep, that's another technique. So you get a little cross to put over the lens of the scope, and that'll create the diffraction spikes for you, but you can also do them in software. So Dennis has got here, the three that he's got here are C85, or the Omicron Velorum cluster in Vela. The next one is C91, which is the Wishing Well cluster, which is also a nice visual target as well. Where are we going? And that one, so C91 is in near the Eta Carina Nebula, and that's about 150 stars in that one. And then the third one along there is the Jewel Box cluster, C94 or NGC 4755. So if you the different designations, C94, they're just different catalogues. So C is the Caldwell catalogue, NGC is the New Galactic catalogue, I think it is, and they're just different catalogues with different objects, so that's why they double up sometimes, and objects have multiple designations from multiple catalogues. And M, of course, is the Messier catalogue of objects as well. Two more by Dennis. NGC, we'll go C96 first, the Southern Beehive, which Dave had a shot of earlier as well. And record in the competition for the furthest open cluster that was imaged was NGC 1966, which was in the Large Magellanic Cloud, and that's about 160,000 light years away. So that little cluster there, which is just in the middle of the image there, is in the Large Magellanic Cloud, and you do need a long exposure photograph to see that one. It's not really visible by eye in a telescope. So well done, Dennis. Thanks for all of those. Michelle got this one of the Wishing Well cluster with the C-Star S50. And finally, Greg sent in this one of the Table of the Scorpion, NGC 6231, which is, again, this is a really nice visual cluster to look at, and a really nice one for the outreach events as well. It's really easy to locate. And it just turns up. This cluster here has actually got some of the hottest and most luminous stars that we see in the sky, and yeah, it really is a great visual target. So the three stars that you see here, they are Zeta Scorpii, which is in the Scorpion's tail. This is actually an area of the Scorpius known as the Table of the Scorpion. And if we see Scorpius here, we've got Antares here and the head and claws of the Scorpion here. And then we've got the back and the tail of the Scorpion coming around here. And over here we've got this little kink in the Scorpion's back. And that's called the Table of the Scorpion, that point there, before the tail comes around and curls back there. And that's where that little open cluster is there. So it's pretty easy to locate. If you're looking at with a telescope, that star Zeta Scorpii is pretty easy to see by eye. Point your telescope there, and right next to it is where you've got that cluster. Now, what happened here? I did have our next target. It was a hidden slide. Okay, our next challenge is going to be Milky Way, and we're looking to shoot telescope free. So we're looking at wide angle shots, no telescopes this challenge. Smartphones will do, but we're looking to get nice wide field views of the Milky Way, and we've got a really nice part of the Milky Way coming up at the moment. So we've got Scorpio up in the sky later in the evening, and then we've got all of Carina and Puppis spanning across the southern sky in that direction, where we can get some really nice wide field shots and capture some of the nebulas and that sort of thing that are in there. So this one here was a 4-panel mosaic that I did last year of part of the Milky Way. So you know, that's what I'm sort of thing I'm talking about. You can go as smaller lens or as wide a lens as you like, but no telescopes. Sorry, it's not putting it up. Because it's hidden. Thanks for pointing that out. That is, isn't it? No, that's not a no scope. Unhide slide. Hang on. It's not in viewing mode. There we go. Just so you know what I'm talking about now. Someone could have said something earlier, you know. All right. At least we're recording, though. We are recording. Okay. That's the photo that I was talking about, and that's the next challenge. So I've said everything I need to say about it. No need to repeat, but there we go. Any questions? It must have been very thorough.
Welcome to Sky for the Month for the rest of April and the first half of May. I'm traveling at the moment, so I'm coming to you from Hamburg in Germany, and I'm at the Hamburg Observatory here. It's a really beautiful site. You can see a massive dome there in the background. That one actually houses a 1.2 meter reflector telescope, very impressive instrument. But we also have quite a few other domes here on the site. So in the background over there, you can see 2 more domes with instruments that are actually open to the public once a month, a bit like our public nights. There's another really big instrument somewhere in the dome over there. That's a 60 centimeter refractor. I think it's the 25th largest refracting telescope in the world. So yeah, it's a really nice site. Unfortunately, it's closed today, so we can't go inside and take photos or videos of the actual telescopes. So I'm going to start, as always, with an overview of the solar system for the next month. So let's have a look at that. So this is the solar system on the 15th of April. It's the Earth around here, with Mercury on our morning side and Venus on our evening side. And we can see that Mars is now reappearing in the morning sky as seen from Earth. If we zoom out a little bit to the outer solar system, we can see Saturn and Neptune very close to the Sun from our point of view. Jupiter still nicely in the evening sky there, and Uranus now also starting to disappear behind the Sun as seen from us. So let's fast forward through the next month or so. So we will see Mercury heading towards its superior conjunction with the Sun, so where it disappears behind the Sun from our point of view. We can also see Venus rising a little bit above the horizon and getting higher in the sky. And we're also catching up with Mars, so Mars will become a bit bigger in the sky as well as rise a bit earlier in the evening. So having a look at that in the all-sky view, so this is the view for the 1st of May. We can see the Sun now setting around 5:30 p.m. and Venus is an evening object, and as we saw just a minute ago, it will actually climb a bit higher towards Jupiter now. So Jupiter is setting a bit earlier, and Venus is rising a bit higher above the horizon over the next month. Jupiter is now pretty low in the northwest, but still the brightest object in the night sky apart from the moon. You can still see Uranus there very close to the horizon, so it is now heading for its conjunction with the Sun on the 23rd of May. For the moon, we have the new moon on the 17th of April, then the next full moon on the 2nd of May, another new moon on the 17th of May, and then the second full moon for the month of May on the last day, on the 31st. So now let's look at the sky around 9 p.m. So we can see that Jupiter now is setting quite early, right? So around 9 p.m. it will have set, or 9:30. So around 10 p.m. now, the brightest stars in the sky now, we can really see Antares here now being very prominent. The Southern Cross and the two pointer stars are very high in the sky in the south around 10 p.m. And we can see that Sirius and Canopus are now close to setting around that time already. If we look at the constellations around that time, again, the Southern Cross here, very prominent, very high in the south. We can see Scorpius now having risen well before midnight, so around 10 p.m. it will be very nicely observable. And we can see Sirius and Canis Major here already close to setting, and Orion now basically gone for the rest of the winter. So continuing on from 10 p.m, you can see for the rest of the night now the Milky Way really prominently in the sky, the core of the galaxy now nicely visible. And then the remaining planets really only appearing towards dawn. So Neptune now rising around 4 a.m. And just after that Saturn, and then a little bit after that Mars. Mercury is now also a morning object, but as I said, it's heading for superior conjunction on the 15th of May. And sunrise now is around 7 a.m. The apparent sizes of the planets, we're getting a bit further away from Jupiter, so that one is now getting smaller. And we see Mars getting a little bit bigger now over the next month or so, or over the next few months. Other than that, a lot of the planets are quite close to the Sun, except Venus, which will be very nice and bright in the sky. We have a few comets in the sky at the moment. So we have C2025 R3 Pan-STARRS, which is around magnitude 5 now. And I've seen a few nice images of that one. C2025 A6 Lemon has faded to around magnitude 11 and should be fading quite rapidly from now. And then another one that we have is 88P Howell around magnitude 9 or 10 and fading gradually over the next few months. And then the one that might have been quite interesting was C2026 A1 MAPS, Sungrazer comet, that actually brightened to magnitude -1 in images from the Solar Observatory, SOHO. So that's a satellite in orbit around the Sun. And that was able to take images of that comet around its perihelion, so around its closest point to the Sun. But we haven't seen any images after that, so it probably didn't survive its close encounter with the Sun. So unfortunately, that one probably won't be visible. Meteor showers, we have the Eta Aquarids coming up from April 19th to May 28th, with a peak on the 6th of May. And these are really dust from Halley's comet, where the Earth is passing through the part of the solar system where Halley's comet left basically a lot of debris on several of its journeys into the inner solar system. So the Eta Aquarids can give us up to 40 meters per hour, and this would be just before dawn. And they could be swift yellow and often have long trains of meteors. Unfortunately, this year they will be very much affected by the moon. So we have the peak on the 6th, and I think the full moon is on the 2nd of May. And as well as the sunlight around dawn, because really the peak happens just before dawn. So we'll have to see whether that's worth observing. Right, so as always, the sources for this month were Stellarium, NASA Eyes on the Solar System, the Astronomy 2026 yearbook, and a source that I forgot to mention earlier was Seiichi Yoshida's Comet page. So this is a really great resource for looking up current comets with like current observations, current magnitudes, and so on. So that's what I'm using now to keep track of the comets for the month. All right, that was all for this month. I will still be traveling next month, so I'll try to find another nice observatory as a background, and I'll see you then.
Tonight's main one is a video about the magnetic universe. It goes for about an hour, so if you want to have a break or go and have a cup of tea or a cup of coffee, just quietly get up at any stage and wander out and wander back in. It's a talk given a couple of years ago by Professor Katherine Blundell, who's an OBE. She's Professor of Astrophysics at Oxford University, as well as at Gresham College, which is like an independent 400-year-old university. And we'll learn all about magnetism.
When ancient man looked to the heavens for guidance from the gods, he noticed star patterns and began to document their movement across the heavens. The ancients believed that the earth was flat, but around 350 BC, Aristotle proved that the earth was round. Later, about 150 AD, Ptolemy presented the geocentric theory, the belief that the earth is stationary at the center of the universe, with the sun, moon, stars, and planets revolving around it in complex orbits. In the 1500s, Nicholas Copernicus of Poland presented the heliocentric theory, the belief that the Earth revolves around the sun as it rotates on its axis. This aspect of astronomy evolved into an intricate study of planetary motion, known as orbital mechanics. Today, orbital mechanics is applied to space flight and satellites that orbit the Earth or travel beyond our solar system. In the early 1600s, Johann Kepler, a German mathematician, using the data on planetary observations collected by the Danish scientist Tycho Brahe, developed 3 laws of planetary motion. Kepler's first law states,
all planets move in elliptical orbits with the Sun at one focus and the other focus empty.
Applied to Earth satellites, the center of the Earth becomes one focus, with the other focus empty. For circular orbits, the 2 foci coincide. Kepler's second law, the law of areas, states,
the line joining the planet to the Sun sweeps over equal areas in equal time intervals.
When a satellite orbits, the line joining it to the Earth sweeps over equal areas in equal periods of time. If areas 1, 2, and 3 are equal, times 1, 2, and 3 are also equal. Therefore, the speed of the satellite changes depending on its distance from the center of the Earth. Speed is greatest at the point in the orbit closest to the Earth, called perigee, and is slowest at the point farthest from the Earth, called apogee. It is important to note that the orbit followed by a satellite is not dependent on its mass. A large, heavy satellite could be in the same orbit with a small, light one, each sweeping out equal areas in equal periods of time. Kepler's third law, the law of periods, relates the time required for a planet to make one complete trip around the Sun to its mean distance from the Sun.
For any planet, the square of its period of revolution is directly proportional to the cube of its mean distance from the Sun.
Applied to Earth satellites, Kepler's third law explains that the farther a satellite is from the Earth, the longer it will take to complete an orbit, the greater the distance it will travel to complete an orbit, and the slower its average speed will be. Isaac Newton, the father of classical mechanics, laid the groundwork for orbital mechanics. He combined the work of Kepler and others to formulate the law of universal gravitation and the three Newtonian laws of motion. While Kepler's laws provided a conceptual model of orbital motion, Newton's laws provided the foundation for the mathematical description of orbits. They explain why a satellite stays in orbit. Newton's law of universal gravitation.
Any two objects in the universe, such as the Earth and the Moon, attract each other with a force directly proportional to the product of their masses and inversely proportional to the square of the distance between them.
Stated more simply, the more massive the objects are, or the closer they are, the greater the gravitational pull between them. Newton's first law of motion.
A body in motion will keep moving at the same speed and in the same direction unless acted upon by an external force.
A satellite moves in a curved path around the Earth because the Earth's gravitational pull acts as an external force on it. Newton's second law of motion.
If the sum of the forces acting on an object is not zero, the object will have an acceleration proportional to the magnitude and in the direction of the net force.
Newton's second law states that force equals mass times acceleration. It is this mathematical equation and the equation for universal gravitation that forms the basis for calculating orbits. Newton's third law of motion explains how a satellite gets into orbit.
For every action, there is an equal and opposite reaction.
If you blow up a balloon and let it go, the balloon is pushed forward by the action of the air rushing out of it. A rocket's exhaust gases are like the air rushing out of the balloon. The following illustrates how a satellite stays in orbit. If a man stands on a mountain and fires a projectile horizontally, gravity will cause the path of the projectile to curve downward and it will strike the Earth. However, if the man fires the projectile fast enough at a specific speed, the curvature of its path due to gravity will match the curvature of the Earth under it. The projectile will then fall around the Earth, becoming an Earth-orbiting satellite. A projectile fired even faster will have a flight path away from the Earth, but gravity will act to slow the projectile down, change its flight path, and pull it back toward Earth. If the projectile's velocity increased enough, a velocity sufficient to escape the Earth's gravitational pull will be reached. This velocity is known as the escape velocity. It is equal to about 7 miles per second at the Earth's surface. The preceding description did not consider atmospheric drag and the Earth's rotation, both of which will affect the trajectory of the projectile. It illustrated the principles governing a satellite's orbit. There are 6 numbers called the orbital elements, which specify the size, shape, and orientation of an orbit in space, as well as the location of the spacecraft in the orbit. Based on an orbit which is an ellipse, the 6 orbital elements are length of the semi-major axis, eccentricity, inclination, right ascension of the ascending node, argument of perigee, time of perigee passage. The major axis of an elliptical orbit is the line joining the perigee and apogee. This line is also referred to as the line of apsides. The first orbital element is the semi-major axis. It is simply 1/2 the major axis. Circular orbits have no apogee or perigee. Therefore, the semi-major axis is simply 1/2 the diameter of the orbit. The semi-major axis is used to define the size of the orbit. From this, the orbital period, or time that it takes for the satellite to complete one orbit, can be calculated. The shape of an orbit is defined by the second orbital element called eccentricity. For all ellipses, the value of eccentricity lies between 0 and 1. The larger the value, the more elliptical the orbit. A spacecraft in Earth orbit with an eccentricity equal to or greater than 1 will escape the Earth's gravitational field. When orienting an orbit in space, a 3-dimensional coordinate system must be defined. The coordinate system commonly used is the geocentric equatorial coordinate system, which has its origin at the Earth's center. This coordinate system is a non-rotating reference system in which a satellite's orbital plane tends to remain fixed relative to the stars while the Earth turns beneath it. The XY plane is the Earth's equatorial plane. The positive x-axis points to the vernal equinox. This is the point where the Sun appears to cross the Earth's equator on its way north on the first day of spring each year. The z-axis is along the Earth's spin axis toward the North Pole. Nodes are points in a satellite's orbit which intersect the Earth's equatorial plane. The ascending node is the point at which the spacecraft crosses the equator going from south to north. The descending node is where the spacecraft crosses the equator going from north to south. The line joining the two nodes is called the line of nodes. The orientation of an orbit is determined by 3 orbital element angles. The right ascension of the ascending node is the angle between the x-axis and the ascending node. It is always measured eastward from the direction away from the vernal equinox in the Earth's equatorial plane. The argument of perigee is the angle between the ascending node and the point of perigee. It is measured in the orbital plane in the direction of spacecraft motion. Inclination is the angle between the equatorial plane and the orbital plane. A satellite which has an eastward velocity component at the ascending node has an orbital inclination lying between 0 and 90 degrees. Such an orbit is called a prograde orbit. A satellite which moves due north at the ascending node is in a polar orbit. Polar orbits have an orbital inclination of exactly 90 degrees. A satellite with a westward velocity component at the ascending node is in a retrograde orbit and has an orbital inclination between 90 and 180 degrees. The 5 orbital elements explained thus far describe the size, shape, and orientation of the orbit in space. The final element is a time value used to locate the satellite in its orbit. A satellite moves in a very predictable manner. It stays on schedule. Thus, if the time at which a satellite passes a particular point is known, the time when it will pass any other point can be determined. The particular point chosen is perigee, and the time of perigee passage is the last of the 6 orbital elements. The 6 orbital elements depict a spacecraft's orbit in non-rotating coordinates. To visualize an orbit relative to the rotating Earth, a projection traces the spacecraft's position on the Earth's surface. The projected path is called the ground track. As a satellite orbits the Earth, the ground track shifts westward. There are 2 causes for this. First, the primary contributor is the Earth's rotation toward the east under the orbital plane. Second, because the Earth is not a uniform sphere and bulges at the equator, its gravity is greatest at the equator. This causes the orbital plane to rotate slowly around the Earth's polar axis in a motion called precession. Precession is toward the west for prograde orbits and toward the east for retrograde orbits. For low Earth orbits such as those of the Space Shuttle at 150 miles altitude, the westward shift of the ground track due to the Earth's rotation is about 22.5 degrees, while the shift due to precession is only about a half degree. The inclination of a satellite orbit determines the north and south latitude limits of its ground track. The minimum orbital inclination is equal to the latitude of the launch site and is achieved by launching due east. For example, if a satellite is launched due east out of the Kennedy Space Center, which is located at 28.5 degrees north latitude, its orbital inclination will be 28.5 degrees, and the limits of its ground track will vary between 28.5 degrees north latitude and 28.5 degrees south latitude. If launch azimuth or direction of flight at launch measured eastward from due north is increased from due east, the orbital inclination angle increases as well as the maximum latitude of the north-south ground track. Therefore, the latitude limits of the ground track equal the new launch inclination. Similarly, if launch azimuth is decreased from due east, orbital inclination once again increases as well as the latitude limits of the ground track. The maximum practical inclination from a Kennedy Space Center launch is 57 degrees. This limit is imposed for safety considerations in order to keep the spacecraft and its booster system from flying over land masses during the ascent phase. To obtain an orbit with an inclination greater than 57 degrees, the spacecraft is launched from Vandenberg Air Force Base in California. Vandenberg offers the opportunity for southerly launches with orbit inclinations between approximately 70 degrees prograde through 138 degrees retrograde. A significant advantage of launching from Vandenberg is the capability to economically achieve polar orbits with ground tracks covering all latitudes from the North Pole to the South Pole. The Earth is constantly turning, and all points on its surface have an eastward velocity, with the greatest velocity occurring at the equator. The farther the launch site is from the equator, or as launch azimuth is increased or decreased from due east, less of the Earth's rotational velocity will be imparted to the launch vehicle. This requires more fuel to get into orbit, or payload weight will have to be decreased. Launches due east from a position on or near the equator, such as the Kourou launch site in French Guiana, used by the European Space Agency, acquire the advantage of a free velocity gain of about 1,500 feet per second. This compares to the approximate 1,300 feet per second gain available at the further north latitude of the Kennedy Space Center. Launching from an equatorial site offers a significant advantage in payload weight capability and minimizes the amount of fuel needed to achieve an equatorial orbit. Since many satellites operate in equatorial orbits, these are important considerations. Spacecraft are launched within a specified time interval called the launch window. Some of the factors affecting the launch window are launch and orbit lighting conditions, sun angles, payload orbit requirements, rendezvous phasing if a rendezvous is planned, tracking and communication requirements, and collision avoidance with other orbiting objects, to name a few. One of the factors defining the launch window for the Space Shuttle is launch lighting conditions, which can be illustrated by plotting time versus day of year. On this plot, we see daylight and darkness at the launch site. The longer daylight hours occur in the middle of the year, summertime. If daylight conditions are required for a convenient emergency landing site for the Space Shuttle, the launch window would now look like this. During the winter months, the available launch window for lighting conditions alone can be as little as 3 hours per day. When combined with the many other launch factors, the launch window becomes even more constrained. The choice of a particular launch vehicle for a mission depends upon the weight and size of the payload and the desired orbit. Expendable rockets used to place spacecraft in orbit usually consist of several stages that may incorporate both solid and liquid propellants for propulsion. When the fuel in each stage is depleted, the spent stage is jettisoned. Staging offers the advantage of discarding weight when it is no longer needed. The Space Shuttle is a two-stage system. At liftoff, the 2 solid rocket boosters and 3 Space Shuttle main engines are all producing thrust. After approximately 2 minutes of flight, at an altitude of 25 miles, the fuel in the solid rocket boosters is depleted and they are jettisoned. The 3 main engines, fueled by liquid oxygen and liquid hydrogen carried in the external tank, continue to burn for several minutes until the shuttle reaches its cutoff velocity. At this time, the main engines are shut down and the external tank is jettisoned. 2 additional burns, using the orbiter's maneuvering system referred to as ohms, are required to place the orbiter in its final orbit. The ohms 1 burn occurs about 2 minutes after main engine shutdown and establishes the orbital apogee point. The ohms 2 burn takes place approximately 30 minutes later and circularizes the orbit. Once satellites are launched and put into orbit, it is often necessary to change the orbit with an on-orbit burn. The common term used in describing on-orbit burns or engine firings is delta V. Delta V is the incremental change in spacecraft velocity measured in feet per second resulting from the burn. The amount of fuel used during a burn depends on the desired delta V change and the mass of the spacecraft. Because the amount of fuel carried is limited, fuel consumption is one of the primary considerations in spacecraft mission planning and is critical to orbit lifetime. On orbit, a spacecraft can thrust in any direction. Burns along the flight path, forward and backward, are the most common. A unique feature of any orbital burn is that if no other burns occur, the spacecraft will later always pass again through the point of burn. Forward burns increase the spacecraft's velocity and are known as posigrade burns. With posigrade burns, the flight path of the vehicle will be raised at all points except the burn point. Burns opposite the direction of flight, which slow the spacecraft down, are called retrograde burns. For retrograde burns, the orbit will be lowered at all points except the burn point. The greater the delta V, the greater the difference between the pre-burn and post-burn orbits. Burns can be combined into maneuver sequences to change orbit size, shape, or orientation. One of the most common maneuver sequences is made up of two burns and is used to accomplish an orbit transfer between two circular orbits in the same orbital plane. The most energy-efficient transfer between two orbits of this type is the Hohmann transfer. The Hohmann transfer is actually 1/2 of an elliptical orbit with its perigee in one of the orbits and its apogee in the other. The burns occur at the perigee and apogee of the transfer orbit. The use of the Hohmann transfer minimizes the delta V required, thus having the advantage of using minimum fuel. The disadvantage of the Hohmann transfer is that it takes longer than most other transfers. The type of the transfer sequence depends on the mission and the amount of fuel available. For example, a space rescue where time is critical might use a fast transfer, while a routine satellite deployment where fuel saved for later use is important would most likely use a Hohmann transfer. The burns discussed so far have all been maneuvers in the original orbital plane and do not affect orbit inclination or node position. There are situations which require an orbital plane change, such as setting up a rendezvous or placing a satellite in an equatorial orbit. To change the inclination, the thrust vector must be directed at an angle to the orbital plane. A thrust with a component that is perpendicular to the orbital plane at either the ascending or descending node will rotate the orbital plane about the line of nodes. A northerly out-of-plane thrust at the ascending node will increase the inclination of a prograde orbit, while a southerly thrust will decrease it. Out-of-plane thrusts require considerable amounts of fuel and are performed only when absolutely required. The Space Shuttle, for example, using all of its onboard propellant, is capable of an on-orbit plane change of less than 3 degrees. Satellite orbital planes and altitudes are determined by their design mission, which very often includes a field of view requirement for optical or communications purposes. The field of view of a satellite is defined as the area of the Earth's surface that is in view from the satellite at any given time. Satellites in high orbits have greater fields of view than those in lower orbits. For example, a satellite at an altitude of 800 nautical miles has a circular field of view with a diameter of about 4,100 nautical miles. A satellite at 200 nautical miles has a circular field of view with a diameter of about 2,000 nautical miles. Low-orbit satellites are often used for photography and other types of Earth observation. A satellite placed in a low-inclination circular orbit at an altitude of about 19,300 nautical miles will have an angular velocity exactly equal to that of the Earth's. The satellite would seem to remain stationary in longitude as viewed from the ground. Such orbits are called geosynchronous and are used to provide a continuous communications capability among any system of ground stations within their field of view. The geosynchronous orbit field of view is constant and is limited to a latitude zone of about 70 degrees north and south of the equator. Effective satellite communications from geosynchronous orbit is not possible at either pole. However, because of their altitude, their field of view covers nearly half the globe. A special type of geosynchronous orbit with an inclination of 0 degrees is called a geostationary orbit. It appears to hover over a fixed point on the Earth's surface at the equator. Most U.S. communication satellites are in geosynchronous orbits, providing near worldwide communications coverage. For effective communications at high latitudes, the Molniya orbit is used. Molniya is the Russian word for lightning and is an orbit used extensively by the Soviet Union for its communication satellites. The Molniya orbit is highly eccentric with an apogee that is near the geosynchronous altitude and an inclination of about 63 degrees. The satellite slows down at apogee in the northern hemisphere and whips through perigee in the southern hemisphere. This provides communications in the northern hemisphere for up to 75% of its orbital period. Several satellites properly spaced in Molniya orbits can provide constant communications at the northern latitudes. Navigation satellites, such as the U.S. Navy's Transit System and the Joint Service Navstar GPS Global Positioning System, use lower orbits so that a user can receive signals from more than one satellite at any time. Another frequently used orbit is known as a sun-synchronous orbit. These take advantage of the precession of the orbital plane caused by the Earth not being a perfect sphere. All sun-synchronous orbits are highly inclined retrograde orbits, which precess eastward around the Earth's polar axis at the rate of 1 revolution per year. Since the Earth-Sun line also revolves eastward at the rate of 1 revolution per year, the orbital plane will maintain a constant orientation relative to the Earth-Sun line. If the satellite's period is then synchronized with the rotation of the Earth, it will pass over the same point on the Earth's surface at the same local time at a regular interval. A sun-synchronous satellite ensures that a constant sun angle and uniform lighting exist for the same field of view from pass to pass. Satellites such as those in the Defense Meteorological Satellite Program and Landsat are sun-synchronous, imaging the entire Earth on a regular schedule. The gravitational attraction of the Earth on a spacecraft causes it to move in its orbit around the Earth. There are other, much smaller forces which will cause a spacecraft to deviate from its desired orbit. These forces cause what are known as orbital perturbations. Orbital precession, which is used to obtain sun-synchronous orbits, results from the perturbing effects of the Earth's non-spherical shape. Other perturbing forces are the gravitational pull of the Sun, the Moon, and planets, and solar winds, which are charged streams of protons and electrons that heat the Earth's atmosphere and increase atmospheric drag. In most cases, perturbing forces can be compensated for in the spacecraft and orbit design and present no major problems. If the forces disturb the orbit too much, thrusters can be fired to re-establish its desired orbital orientation or altitude. This is particularly true for spacecraft orbiting at very low altitudes, where the effects of atmospheric drag are greater, and, if not compensated for, will eventually cause the spacecraft to deorbit. A spacecraft's operational lifetime is frequently limited only by the amount of fuel available to maintain its desired orbit. When its useful life is complete, a satellite is left in orbit or is deorbited, burning up when re-entering the Earth's atmosphere. When the Space Shuttle completes its orbital mission, it executes a precise retrograde burn to initiate its controlled return to Earth. This burn occurs nearly halfway around the Earth from the landing site. The new orbit established by the retrograde burn causes the orbiter to enter the Earth's atmosphere about 4,000 miles from the landing site. During the period the orbiter descends from its orbital altitude to atmospheric re-entry, its attitude is maintained by the use of reaction control jets located in the nose and tail of the orbiter. Once the orbiter enters the Earth's atmosphere, its wing and tail aerosurfaces begin to become effective and gradually replace the jets for attitude control. As the orbiter nears the landing field, it maneuvers to a long, straight-in approach at an angle of 17 to 19 degrees. Nearing the runway, it executes a flare maneuver to reduce its sink rate and glides to a touchdown at approximately 230 miles per hour. As the orbiter rolls to a stop, our journey into the world of orbital mechanics comes to an end for now. This is only the basics of orbital mechanics, an intricate study of planetary and satellite motion. The next time you see a launch, you will see it from a different, somewhat knowledgeable perspective. You will understand the fundamentals of spaceflight.
Now, before we close, we'll look at Earth's Van Allen radiation belts that were first looked at by NASA's SAMPEX mission, and then a little bit later by what became known as the Van Allen probes mission. This footage is courtesy of the Goddard Space Flight Center and also their scientific visualization studio, and the audio that you hear is Sunrise by Mocha. Now, the first footage from 2003 is from the Solar Anomalous Magnetospheric Particle Explorer, or more commonly called SAMPEX. It was launched in 1992 and was shut down in 2004 and then re-entered Earth's atmosphere in 2012. Now, that was an uncontrolled re-entry as the fuel had been fully used up at that point. Then later on in the clip we see the 2012 footage from the radiation belt storm probes, or RBSP, which were later renamed just to be the Van Allen probes. There were two of those launched at the same time, both travelling in the same orbit and very close to each other in the orbit that you'll see in the video coming up. Now, these two probes were launched together in 2012 and were turned off in 2019. The first of them actually re-entered Earth's atmosphere about a month ago in March, and the second probe, the Van Allen probe B, will actually re-enter sometime in the 2030s, so not entirely sure when, because these are uncontrolled re-entries, so the fuel has run out, and it will depend a lot on the solar activity between now and then, and how much Earth's atmosphere expands and contracts and maybe brings it down slightly faster. Now, one thing that you'll notice, so if you look on the right hand side, the top picture is the SAMPEX mission, and you see the technician for scale on the left hand side of it, and the slightly bigger one on the right hand on the bottom right of the screen is one of the two Van Allen probes shown there. Now, you'll actually hear what the Van Allen probes recorded in terms of plasma waves from the solar wind as they pass around Earth's Van Allen belt. Of course, Earth's Van Allen belts are quite dangerous to astronauts if they're passing through, and there's a solar storm at the time, because the charged particles from the solar storm are effectively ionizing radiation, and they'll get trapped in Earth's Van Allen belts, and you don't really want to be there at the time. And this was one of the concerns of not only when they sent Artemis to the moon, but of course also the Apollo missions, that you had to travel for about I think it's about an hour and a half to actually get through the danger zone. Now, at the end of the video, you'll hear the sound of the plasma waves, and you notice from the orbits, when you look carefully at the twin probes, that they travel very close to each other, and this is by design, so as to look for very short-term changes in the Van Allen belt's structure. So, whereas if you only sent one probe, it would have to go once around its orbit, and by the time it got back to the starting point again, whatever was happening there has well and truly passed. So the idea is to look for any short-term changes, and that's why they launched two at the same time. Okay, and with that, we'll close the April meeting, and hopefully I'll see you all with the May meeting.